Ladies and gentlemen, welcome once again to the Simkins Physics Corner. It's me, Mr. Simpkins, doing physics in a corner. Today's topic, dynamics. Dynamics is when we look at forces to describe how things move and why things move. And today we have quite a doozy for you. Now let's get started with step one, which is understand the question. We have two wooden crates. They're tied together by this cord, and another cord is tied to the first crate and exerts a force of 185 newtons at an angle of 20 degrees as shown below. Each crate has a coefficient of kinetic friction of 0.55, which is just a number that tells us how much friction we have. Find the tension in the rope between the crates, so the FT in there, and the magnitude of the acceleration of the system. I'm only asking you for two things. It can't be that bad, right? Well, we're going to have to flex our algebra muscles a little bit on this one. But if we use free body diagrams, which is a drawing to represent the forces acting on an object, we can start to work our way towards these tension forces and the acceleration. You see, an unbalanced force causes a mass to accelerate, and if the forces are balanced, then there's no acceleration. And so the strategy we use is Newton's second law, sigma F equals ma, which means the sum of the forces in a particular direction cause a mass to accelerate, or not, if the forces are balanced. The other main principle that, or at least the equation we need to know, is FF equals mu Fn. All that tells us is that the magnitude of the force of friction between two surfaces is determined by this mu, this coefficient of friction, mu, and the normal force, which makes sense if you think about it. Mu tells us about the two surfaces rubbing together. So if it's really slippery, the mu will be really low. If it's really rough, the mu will be really high. And then the normal force is how hard are you pressing down. Imagine sliding something across the table and then pushing down on something while sliding it across the table. When you push down, there's going to be more of an upward force, and there's going to be more friction. All right, so that's the second thing we need to know is the force of friction equation. And then as we continue forward here, we may need to throw a couple other things in here. So let's go ahead and start with our main strategy. I'm going to start with this block. We're going to call this block 1. We're going to call this block 2. And I'm going to start with block 1. You'll see why in a minute here. If I think about the sum of the forces in the horizontal directions on block 1, let's take a look at that. Well, horizontally, all I have is the tension point to the right and the friction resisting that motion to the left. So what I can do here is I'll assign to the right as a positive. And so therefore, the forces in the x direction on box 1 would be Ft minus Ff, because Ff is moving to the left, and we've assigned positive to the right, equals m1a. All right. Now, we can break this down a little bit because of what we know about the force of friction. We can take it to this next step, Ft minus mu Fn. I'm going to make a substitution here, mu Fn. The reason I did that, again, you can reference this equation right up here, equals m1a. Now, we kind of get stuck here in this direction for this block. So what I'm going to do is also take a look at the sigma Fy. The sigma Fy. In fact, I'm going to do it up here because I'm going to need that space later. Sigma Fy for mass 1 of A. Now, you notice in the y direction, there are only two forces. There's the force of gravity down, and there's the normal force or the pressing force of the surface pushing back up. And since there are no other vertical forces, and the problem doesn't say that we're either floating up into the air or going down into the ground, there's no vertical acceleration, which means the acceleration here is 0. And if the net force in the y direction is equal to 0, then that means that Fn plus Fg equals 0, or in other words, the normal force is equal to the negative version of the force of gravity. This is the last thing that I remembered that we needed to know, is that the force of gravity is found by taking an object's mass and multiplying it by the acceleration due to gravity. So if we do that, that tells us that the normal force is equal to negative mass times negative 9.8, right? And the negatives will cancel out here. Effectively, what that means is, in this spot, back in our x direction, while we can't blend x and y forces, we can take what we know from the y direction and maybe apply it to the x direction. Let me show you what I mean. If we know that the normal force has a certain size, m times 9.8, in this case we actually know the mass, it's right here, well then we can plug that in over here. And so our final little expression here, before we move to the second block, is going to be Ft minus mu m1g equals m1a. And since this problem is asking us to solve for acceleration and tension eventually, I'm going to solve for acceleration in this expression. all I would have to do is divide both sides by m1, and that would get me accelerations equal to ft minus mu m1g divided by m1. Now, you'll notice we know mu, we know m1, and we know g. So the only two unknowns are our a and our ft. We have one equation with two unknowns, and both of them are the things we need. You may think to yourself at this point, well, guess we should call it a day because we're stuck. But the one thing that helps us here is the rule that tells us that the tension in a string is the same at all points throughout a string, which means the ft to the right on block 1 is going to have the same magnitude as the ft to the left on block 2. So if I represent the forces on block 2, there are actually two moving to the left. There's the friction between the ground and the block, and there's the tension of the string pulling backwards. Then, of course, there's also going to be another force acting horizontally but to the right. Now, you may be saying, well, Mr. Simpkins, I don't see a force going to the right. Well, we would agree that this force is going both up and to the right, and we use what we know about vectors from our previous unit in order to find the components of that force. So if I had to sketch it like a triangle, this would be the x component of that force, and this would be the y component of that force. And so I'll call this Fx. And then, of course, vertically, we would have Fg down. We would have the normal force up. And again, because of this pulling force that's going up and to the right, we actually also have another force acting upward. I'll call that Fy. That's the y component of the force that's pulling over there. As you can tell, this free body diagram is much more complicated than the first one, which is why I started with the first one, by the way. But let's see if we can use the sigma f expressions to inform us any more about this second block. If we look at sigma fx equals ma, let's consider the forces in the x direction on block 2. We have fx, as we call it here, minus ft minus ff equals m2a. You see, this is the second mass, so I want to make sure I know which one I'm talking about when we combine our equations later. Now, fx, fortunately, we can just do f applied times the cosine of theta, so that would eventually be our 185 times cosine of 20, minus ft, don't know it, that sucks, minus mu fn equals m2a. Now, on the block 1 side of things, we were able to find the normal force because it was just equal to the force of gravity. But we can't say that the normal force is equal to the force of gravity for block 2 because, look, normal plus Fy equals Fg. There's no way that Fn could then be equal to Fg. But let's take a close look at the y direction to see if we can find anything out. What I'm going to do is I'm going to park this equation, but I'm actually going to solve it for a just like I did over here for the other block. And so I'll just write this expression. It's going to look a little long and complicated, but keep in mind we actually know a lot of this stuff already, which is helpful. So mu fn divided by m2. I'm going to come back to that one in a second. Let's consider the vertical forces acting on the block 2. Now, the saving grace of this problem is that the first block is not lifted up off the ground by this pull. It's moving exactly horizontal, which means there's no vertical acceleration. And that means that the sum of the forces in the y direction is 0. So if we consider this up here, just visually, we would have the normal force plus the y component of the applied force equals the force of gravity, right? These two up have to equal this one down because we're not accelerating, so we need balanced forces. And the nice thing about that is if I solve for Fn, that's going to be equal to m2g, notice I specified because we're considering the second block, minus f sine of theta. Fy, the y component of this force, would be used the trig f sine of theta. Now, I hope you just got excited because, as you can see, we actually can numerically figure out what the normal force is on block 2. All right? We couldn't necessarily do that. Actually, we could have done that over here, but we didn't yet. So let's go ahead, and I know you guys love throwing numbers in here, so let's go ahead and throw some numbers. All right? M2 is going to be 12.1. Your numbers may vary. Times 9.8 minus the force is 185 sine of 20. Okay. And so we get our calculator here. We got 12.1 times 9.8 and then minus 185 sine of 20. Yesterday I was doing this problem in radian mode, and as you can imagine, that made all of my answers wrong. So make sure you're in the correct mode on your calculator when you're typing in angles. 55.3 newtons. Okay, well, that's going to be an interesting piece of information. Now, here's the big algebra leap that some of you are going to really hate, but it's not going to be that bad once you plug the numbers in. Block 1 and block 2 are tied together. That means that they accelerate at the same rate. So while they have different masses, the acceleration of block 1 is going to be equal to the acceleration of block 2. They're tied together. And if this acceleration equals this acceleration, I can use what's called a system of equations. If this is acceleration and it's equal to this quantity, check this out. Acceleration is ft minus mu m1g over m1. That's what we learned from block 1. But from block 2, we learned that acceleration is also equal to all of this stuff. F cosine theta minus ft minus mu fn divided by m2. Do you see what just happened? If both of these expressions are equal to a, then I can set these two expressions equal to one another. This is what we call using a system of equations, or substitution. Now you look at that and you're like, how are we any closer to solving this problem? Well, if you look hard enough, in both of these sides of the equation, ft is the only thing that we don't know. Everything else we have the numbers in our back pocket for. So now is the fun part where we plug and chug and we see if we can find the answer. So let's go ahead and do that. ft minus mu 0.55 m1. Now you see why it was so important that I labeled my stuff earlier. So when I pull everything together, I remember what numbers go where, times 9.8. Okay, divided by m1, which is 9.57, equals, all right, we have our applied force, 185 cosine of 20 minus ft, don't know that one, minus 0.55, Fn was 55.3 newtons, already solved that one, over m2, which is 12.1 kilograms. Okay, it's getting a little out of focus. Just a tad. There we go. All right, so from now it's just grinding, it's just doing your algebra, it's just making sure you're careful with all of your math. But eventually what you can see here is that you can move all the terms to one side, you can move all the terms to the other side, and you can solve for ft. So let me just combine a couple of things here for you. 0.55 times 9.57 is 9.8. All right, so on this side we end up with ft minus 51.58 over 9.57 equals, I do 185 cosine 20, and you notice that's going to be subtracting this from it, so we do minus 0.55 times 55.3, and that is going to get me 143.43 minus ft. All right, what I just did is I just combined this and this together. They end up adding up to that number. That's divided by 12.1. You can use a variety of mathematical strategies at this point. You can cross multiply as the first step if you want. Sorry, this is so fuzzy. I'm really trying to get this focus for you. There you go. So if I cross multiply, I get 12.1 ft minus 51.58. So that was that cross multiply right there. That's going to be equal to 9.57, 143.43 minus ft over nothing. I cross multiplied, so that's good to go. And so then we can eventually get our ft out of here. We got 12.1 ft minus 12.1 times 51.58. I'm sure there's a more efficient way to do this. I'm kind of doing it the brute force way. If you have a better way, you can drop it in the comment section. 9.57 times 143.43. And like I said, there's a lot of algebra in between here and there, but eventually you'll get to this point. Now we want to combine the ft terms on both sides. So to do that, I would add 12.1 plus 9.57 to get a total of 21.67 ft over here. I would get 1372.6, and I'd have to add plus 624.12. Gets me 1996.72. And it looks like I might run out of time in this 15-minute video window to solve the answer for you, so I guess I'll have to come back. Let me pause. the algebra, find the answer, plug it into this equation, and you got your